Okay, hi everyone, and very pleased to be here and to present C12. We are building reliable quantum computers, and so we are a very unique approach using carbon nanotube qubits. So let's start with C12. We've been funded in 2020. It's Paris-based quantum hardware startup. It's a technology from the École Normale Supérieure in Paris. We are now 24 employees. We raised the seed round last year, so we are still an early stage startup. And we worked on the first application on quantum chemistry and optimization. So our vision on why to use a carbon nanotube to build a ultra long current time and scalable quantum computer. So the biggest challenge of this industry, the quantum industry, is to fight errors. And all the errors, the quantum errors, what actually makes quantum calculation not useful, they come from defects in the qubit material. And there is actually a large consensus in the scientific community that if we want to build a large-scale quantum computer, we need some breakthrough in the material. So a quote, for example, from a great scientist I admire, Chris Monroe. So he's not developing a quantum computing platform that is identical to C12, but what he's saying is that if we actually want to build a solid state qubit quantum computer, which is what we are doing, this relies on breakthrough in material science. And we have, after years of research, selected the carbon nanotubes. So they're actually incredible material. They have extraordinary properties to make them qubits. So in a way, we are like transforming a carbon nanotube into a quantum transistor. So if you take the other approaches, superconducting qubits, which is good, is that they rely on semiconductor fabrication techniques. The problem is that they have reaching their limit in terms of current time, and they are posed by crosstalks, so limiting them to scale. Another technology raised a lot of attention. It's ion qubit. So here, the qubit lies in vacuum, so you have a very good fidelity. The problem is that you need some microscopic trap for this qubit, and so it's not a scalable technology. What we have with carbon nanotube qubit is that we bring the vacuum feature, what makes very high fidelity, because at the end, our qubit, which is a spin qubit, doesn't see anything else than a few hundreds of carbon atom, very pure carbon atom, on a semiconductor platform, which is easy to scale because it benefits from all the like semiconductor fabrication techniques developed by the semiconductor industry. So here is what our spin qubit look like. So first you start with an ultra pure carbon nanotube connected between two contact electrode, and they are suspended about a gate of array electrode. Those gate electrodes, they form a double quantum dot that trapped a single electron. So here, when you have like this single electron into a double quantum dot, you have a charged qubit. And then we use a magnetic gate to untoggle the electronic spin with a charge. And we manipulate actually the spin through a microwave pulse. So this is also what is very interesting with this technology is at the end, you control and read out